We begin this module by completing our construction of the real numbers. So we recall from last module we had defined Dedekind cuts, which are a subset of the rational numbers satisfying three properties. Satisfying properties which we called C1, and so that A is a cut if A is not the empty set and A is not all of Q. Okay, so the empty set cannot be a cut and neither can be Q. C2, if R is an A, then if Q is some other number in Q with Q smaller than R, then Q is also in A. So if you find a rational number that is smaller than an element in A, then the rational number must be in A as well. And the final property was probably that A doesn't have a maximum. So if R belongs to A, there must be a bigger number. Then this implies that there exists an element S in A such that R is less than S. So this property is usually referred to as not having a maximum. No Dedekind cut can have a maximum. Okay, and so our candidate for the real numbers, is a set which we denote R. I mean, we're using the same notation for now, but for now this is just a definition of a candidate for real numbers. So this is going to be the of all Dedekind cuts. Okay, so there are many properties that we want from R, and those that are shared by Q. So we want it to be an ordered field, and we want be an ordered field, but most importantly, we want that, which is, Q is already an ordered field. What we want as an additional property, want that R satisfies the least upper bound property. Okay. And finally, otherwise we would not be extending Q, but just creating some other object completely unrelated to Q. Or to contain Q. And here I put it in quotes because what we're really doing is identifying a subset of the Dedekind cuts with irrational numbers. Identify Q with a subset of R. So the new operation plus and so summation and multiplication are compatible with the original ones. We also want the order in Q to be preserved under the map to identify the elements of Q with some Dedekind cuts. This means that if number Q1 was smaller than a number Q2 in Q, then once you map those Q1 and Q2, then Q1 is still less than or equal to Q2, but with a new less than or equal order defined in R. Okay? So there's many restrictions that we want and many properties we want of R. Fortunately, everything is done in an intuitive way. So we define R in such an intuitive way, and all the operations plus minus, which will come for free, the product, and also the new ordering that will impose or you will define in R. We'll define in a natural way so that these naturally extend those corresponding operations and ordering in Q. Okay, so we start by defining the ordering in Q, in R. So we could let A and B be Dedekind to Dedekind cuts. Then we denote A less than or equal to B. So we're using the same notation for the order less than or equal to in the rational numbers. To mean A is a subset of B. Okay, remember, this is just notation. We're defining an ordering in this subset of the power set of Q of Dedekind cuts. This is just notation. Remember, this is just notation that is that should be it should give us an idea what's going on and how we are trying to extend the notions of ordering inside the real numbers. Okay, so one of the exercises you have, which is 8.6.4, is to verify that this is indeed an ordering. I mean, if we define ordering in this way, then we should have the properties of ordering. That's exercise 8.6.4. Which states that which asks of you to show that this defines an ordering from our candidate for the real numbers. So this means that we need to verify three properties: O1, O2, and O3. Okay, I'm just gonna go over these properties and give you an idea. I mean, you have to complete all the details. I mean, that's part of your homework. And so I think we all agree that O2 is true because if A less than or equal to B and B is less than or equal to A, this means, by definition of this ordering, this means that A is a subset of B and that B is a subset of A. But these two things, in A being a subset of B, is the same as A being less than or equal to B, and B being a subset of A is the same as B being less than or equal to B. So these two things put together implies, if you remember set theory, that A is equal to B. Now, for O3, if A is less than or equal to B, and B is less than or equal to C, then we know that A is a subset of B, and B is a subset of C. Putting these two things together, we arrive at the conclusion that A is a subset of C. A is containing B, which is containing C. So again, by simple manipulation of the propositions of A being a subset of B and B being a subset of C, we get the transitivity that we would expect. Okay, that means that A is a subset of C. But this is the same that A is less than or equal to C in the new order. Okay, and so you see now that O2 and property O3 come basically for free from the set theory, from knowing the properties of sets, following set theory. Unlike these two properties, which, as I said, just come from simple facts of propositional logic involving sets, property O1 really asks you to use the fact that A and B are cuts, because this is not true for subsets of a given set of Q or anything in general. So O1 really you to use the facts that you are dealing with cuts and not just any subsets of the rational numbers. For instance, you can have, say, a set A and a set B, and neither A nor B contains the other, right? But this is not true in the case of cuts. And this follows from the property that we have over here, the property defining cuts, property C2, that if a rational number is in a cut, then all the smaller numbers are there as well. Okay, so that's where you can make the distinction between just any two subsets of the rational numbers. Okay, so this this video is getting pretty long, but so let me just conclude by saying that, well, then when typing down the proof of the property O1, you have to be very careful, and you really need to use the fact that the sets involved are cuts. Okay, that's it. So that we meet again in the next video.